start. Okay, so I'm going to do this lesson a little bit through this whiteboard. We'll see how we go. So if I write it on the whiteboard, it's like me writing it on the board at school, and it's kind of stuff that I would encourage you to make notes about. So we're going to start a new topic today. It's actually the start of a series of topics. So we're going to do electric fields, followed swiftly by magnetic fields, and then we're going to stitch the whole lot together to form a theory of electromagnetism. This is going to take us a little while, so ease into the topic nicely. We'll probably be on it most of the way to Easter, if not till Easter itself. And it really is kept as pretty much our last topic because it's the one that is closest to university level physics and is the one that's going to stretch your physics understanding as far as we're going to at A level. So that's why we saved this one for last. So it's not beyond you. It's not going to be too difficult for you. It's just that we needed loads of prerequisite knowledge before we could get going on this one. You need to be able to pull lots of physical ideas and concepts together in order to understand this topic. So that's why we've left it till practically the last topic. And hopefully you'll get something out of it, whether you're going to go on to do more physics or not. We're going to start our study of electric fields with the electric force, in particular, the electrostatic force. So you are by now familiar with the fact that all matter has got fundamental properties, such as the gravitational mass and the inertial mass, which appear to be the same thing. And you are also familiar with the fact that matter has a property called electric charge. The origin of electric charge is unknown. It is just a fundamental property that all matter appears to have. It comes in different values, so you can have different amounts of it. And it also seems to come in two different types, which we'll come on to in a minute. But in order to study the electric force, we need some charged particles. So originally this was done by taking some objects, normal-sized objects, like apple-sized objects, and charging them up. So the easiest way to do this historically was to take an insulator like plastic or resin, amber, something like that, and just polish it with a cloth. And this would convey what was called static electricity to the object. You're familiar with this from GCSE. And so simple friction can transfer electric charge to objects. And so the diagram in front of you represents two spherical objects, which can be actually spherical objects, or it can be point-like objects if you prefer, but two objects that have a net amount of electric charge on them. So the object on the left has got an amount of charge Q1, and the object on the right has an electric charge Q2. And this is a perfectly good experiment that can be conducted. And then what you can do is place them a distance apart from each other. And that can be a known distance, because if these really are two apple-sized spheres of plastic, then you can obviously take a ruler and measure the distance between their centers. And then they will, it turns out, we observe, push each other apart with a force F. And by Newton's third law, that force F will be the same force on each object, but acting in the opposite direction, as drawn in the diagram. The way this experiment is done in order to measure the force is usually, you don't need to draw this bit, we would dangle the two objects. Looks like I'm drawing some kind of cherry or something. And the force would push the strings that the two objects are dangling from away from the vertical, and we can measure that angle at the top, and then we know the mass of the spheres, so we can work out the weight pulling them down, and then by doing a little bit of resolving vertically and horizontally using the tension in the string. So if we resolve vertically, we can find the tension in the string. This vertical component of the tension will be equal to the weight. And then if we take the horizontal component of that tension, that'll give us the size of the force. So this force is measurable. The charge and the distance are both measurable. Certainly the charge is very measurable these days. Historically, it was very difficult to do, but these days much has been done in terms of electronics, in terms of producing Coulomb meters that can measure the amount of charge on things. And through experiment, it is possible to deduce the following relationships: that the force is directly proportional to the charge on the one object, and, as you would expect through symmetry, also the charge on the other object as well. There's no reason to favor one object over the other. This is a symmetrical relationship. And also that the size of the force reduces with the separation. So as the charges get further and further and further apart, the size of the force reduces. And indeed, if you were to take them an infinite distance apart, the force would become zero, as you would expect. It turns out that doubling the distance quarters the force, and therefore it's not a 1 over r relationship, but it's a 1 over r squared relationship. And this should be familiar to you from the gravity topic that we did, in which a very, very similar arrangement took place, in which these were the masses of two objects, and again it was an inverse square law. The difference between this and gravity at this stage is that these were attractive forces when we were talking about gravity, but now this is a repulsive force. And so, yes, there is a similarity with gravity in the form of the equation, but also a distinct difference in that this force is a repulsive force. But more than that, it was also discovered that charge comes in two different types. And what we could have done was given them two different names, like blue and green, or up and down, or left and right. But we chose to give them two names that would work mathematically. So we can turn this into an equation by writing F equals some constant of proportionality, and then combining the variables. And then to make it into a vector equation, we would just need to point out that this force F is in the direction of the vector from Q1 to Q2. So we could put a little unit vector there, just like we did with gravity. And then this becomes an equation that the sign will reverse the direction. So when we were choosing how to label our two charges, we decided to go with positive and negative, literally as positive and negative numbers, because if Q1 and Q2 are both positive, then a positive times a positive is a positive overall, and therefore this vector remains in the same direction. If both charges are negative, then again, a negative times a negative is a positive, and this overall remains positive, and so this is in the same direction. It's still a repulsive force. But if one of the charges is positive and the other charge is negative, then what we have instead is that a positive number times a negative number is overall negative. And so the minus sign that would result from this calculation here, that minus sign belongs to the vector, and it reverses the direction of the force, so that instead of the forces being repulsive, it becomes attractive. So charged particles can act in an attractive manner using the electrostatic force, but you need the two charges to be opposite in type. Now, I already said at the beginning that we have no idea why electric charge exists in the first place, so we certainly have no further idea about why electric charge exists in two different forms, positive and negative. But it does, and we have our statement of what is known as Coulomb's law to describe how it works, that the two charges multiplied together, divided by their separation, multiplied by a constant to turn the whole thing into newtons, will give us the force of either attraction or repulsion. Attraction, if they're opposite charges, so that there's a minus sign around to reverse the direction, or repulsive if both charges are positive or both charges are negative. So this statement here and the words that I've just given you with it are what's known as Coulomb's law of electrostatic. And Coulomb is the same Coulomb that we named the unit of charge after. So I'm just going to give you a moment or two to finish writing that down if you need to, and in particular to make the statement that if Q1 and Q2 are oppositely charged, the force is attractive, but if they are similarly charged, it is repulsive. Okay, now if we were in the lab, we could do some experimenting with this. So I could take a couple of metal spheres and I could dangle them from a string or two strings, and I could charge them up using the high voltage power pack, and we could watch them push each other apart. However, these days a much more accurate way of investigating Coulomb's formula would be to attach them both to plastic supports to insulate them, and then attach one of the charged objects to a top-down balance, and then the other object just to a retort stand above it. And then what I would be able to do would be to measure the increase in mass. And if you look in the textbook later on, there's a diagram that shows you that setup. The point is that this formula is something that can be investigated. So we can measure Q1 and Q2 and R and F, and by doing that, we can determine what this constant of proportionality is. Now, when we were looking at some of the things we've looked at in the past, it's been possible to choose a really lovely constant of proportionality by correctly choosing the units. But by the time Coulomb had put his law together for this, the unit of charge had already been fixed, and the Newton had already been fixed, and the meter had already been fixed. And so there wasn't any wriggle room with the definition of the units to make this into a lovely constant. It turned out to just be whatever we had to measure it that could successfully turn coulombs and meters into newtons. So this constant of proportionality, when you measure it in an experiment, turns out to be quite a nice number, actually. It's pretty much 9 times 10 to the 9, which is an easy to remember number. And certainly students the world over, I'm sure, would love it if 9 times 10 to the 9 was the number that we used. To put some units on that, we just need to get rid of the coulombs and the meters and add in some newtons. So this is our constant of proportionality K, 9 times 10 to the 9. Okay, some historical context now. Coulomb was doing his work on his law in the late 1700s. But 100 years after that, after his law had been properly established and people had been using it for a long time, and the 9 times 10 to the 9 was working very well, about 100 years later, a Scottish theoretician called James Clerk Maxwell took Coulomb's law, and he glued it together with some other things that had been discovered since. So he glued it together with some ideas about electric currents and some ideas about magnetism, and he produced what are now known as the Maxwell Equations of electromagnetism. And as I said to you, we will move forward to study the interaction between electricity and magnetism, and we will hook them together to produce electromagnetism. We're not going to study Maxwell's equations because that's firmly university level physics, but I will show them to you and we will mention them. The point of me telling you this is that 100 years after Coulomb established this law, it kind of just became a subset of the Maxwell equations. And the Maxwell equations became this wonderful cornerstone of physics, which describes all of electric and magnetic phenomena. And so it was much more important for the algebra of the Maxwell's equations to be straightforward and transparent and as efficient as possible. And when Maxwell formulated his equations using Coulomb's law, he found that throughout his equations, there was a 1 over 4 pi k everywhere throughout the Maxwell equations. And it got to the point where Maxwell realized that in the Maxwell equations, K never really turned up on its own. It was always as part of this composite number, 1 divided by 4 times pi times K. And so quite reasonably, Maxwell said, you know, it seems ridiculous to maintain the use of K when all that's happening is that every single time I write a K, I write 1 over 4 pi next to it. And so quite reasonably, Maxwell said, look, we need to abandon this K because the only time it actually ever turns up is in Coulomb's law, and we've absorbed that into the Maxwell equations now. So Maxwell gave this constant a new symbol. It's called epsilon naught, or epsilon 0, but it's usually pronounced epsilon naught. And epsilon naught is the permittivity, got a cool name, permittivity of free space. Not to be confused with mu naught, which was the permeability of free space from the last topic and capacitance. So let's not muddle it up with mu naught. This is epsilon naught, the permittivity of free space. And what that means is that if we're going to use epsilon naught as our fundamental constant of the universe rather than K, then that means that K is now equal to 1 over 4 pi epsilon naught. And so students like yourselves who are learning about Coulomb's law now, some of you may choose to go on and study the Maxwell equations in greater detail later, in which case we need to prepare you for that transition now. So in your A-level physics, we're not going to be using K. We're going to be using it as you will use it if you were to go on and study further physics after this. So it's an inconvenience for A-level students that actually K is not the value that appears on your data sheet. What actually appears on your data sheet is 8.85 times 10 to the minus 12. And it even has funky units to go with it, which is the farad per meter. Which means whenever you want to do a calculation using Coulomb's law, unfortunately for you, you have to tap in 1 over 4 pi times 8.85 times 10 to the minus 12 into your calculator, which is a lot more cumbersome than simply writing 8.89 times 10 to the 9. I've tried to justify why that is done, though. It is not anything that will help you during your A-level. It's just laying the groundwork for the next step if you were to take it. Okay, so this is actually how Coulomb's law is stated in textbooks and formula sheets and exam questions and revision guides and anywhere else that you would choose to look for it. So 1 over 4 pi epsilon naught Q1 times Q2 divided by R squared. Okay, so shall we do a practice question to see if you understand quite how big the force is or how small the force is? Let's find out. So let us work out what the force of repulsion is between a pair of protons in an atomic nucleus. So hopefully you will recall that the charge on a proton is the elementary charge, 1.6 times 10 to the minus 19. So E is not standing for electron, it's standing for the elementary charge. So each of your protons has that charge. The radius of a proton is 1.2 times 10 to the minus 15. So we're going to need 2 radii because the protons are that distance apart. 1 radius plus another radius. So those are your 2 numbers that you need for your data. Could you please tap those into this formula and work out what the force of repulsion is between a pair of protons in an atomic nucleus? So when you finish doing that calculation, you should find that the force of repulsion between 2 protons in a nucleus is 40 newtons, which really isn't very much. I don't know, what, a can of beans must be something like 40 newton. No, a bit more than that, isn't it? Maybe 4 cans of beans. I guess each one's about 10 newtons. I mean, you could pick that up quite easily with your arms, couldn't you? It's not that big a number. But then you have to remember the whole point of forces is that they make objects accelerate. So the next little thing that I would like you to ponder on is what would be the acceleration on those pair of protons if the force was actually able to act on them. So if they could hurtle apart, what would be the acceleration they would experience? And you're going to need the mass of the proton, which is 1.67 times 10 to the minus 27. Okay, so that's a big number. 10 to the 28 meters per second per second. That means after a single second of acceleration, those protons will be flying apart at 10 to the 28 meters per second. Now, clearly this is not possible because that is orders of magnitude, 20 orders of magnitude faster than the speed of light. My point is that within a fraction of a second, those protons will be flying apart at the speed of light, which is ridiculous. To have a force that powerful that if you take two of the least charged objects in the universe, so a single proton and another single proton, you can't really get much less charge than that. And you just place them side by side, and the force is so powerful that it can accelerate the least charged objects in the universe up to the speed of light in a fraction of a second. It is ridiculous how strong the Coulomb force is. And that constant at the front, that 9 times 10 to the 9, plays a large part in the strength of the force. Not all of it, but a large part of that. It's a big constant at the front of that force law. We will come back to pondering upon this in more detail in the future when we revisit the atomic nucleus and I remind you about the strong nuclear force. You might remember it already. I mean, we have done this calculation once already, but it was back during the last lockdown, and I don't know how much of that you'll have retained. But what I would like to just pause before we go forward is just compare it. And again, this is a calculation we've done. Compare it to the attractive force of gravity that is pulling the two protons together. So we've got a repulsive force of 40 newtons. What I'd just like you to do now is work out what the attractive force due to gravity is. So if you remember your gravity formula, it's gmm over r squared. And so you're going to use the mass of the proton, same separation as before. Your gravitational constant, if you remember, is 6.67 times 10 to the minus 11. Hello, just realized that I'm muted. How long have I been muted for? I probably haven't said anything about the 10 to the minus 35, have I?
No, it was since you told us to do the calculation.
Yeah, okay. So the 10 to the minus 35 here is very, very small compared to the 10 to the 2. Orders of magnitude different, getting on for 40 orders of magnitude, which is just ridiculous. In large part, it's due to the constants. The constant on this one is 10 to the plus 10, 9 times 10 to the 9, whereas on this one, it's closer to 10 to the minus 10. So the constants alone have a difference of 10 to the 20. And you're never going to find any masses that are big enough and close enough together that they are attracting each other with such an acceleration that they're up to the speed of light within a fraction of a second. That's just not a gravitational thing. Gravity isn't powerful enough. The only reason that we pay no attention to the electric force generally is because we are in a situation where the electric force is so utterly powerful that every positive charge in the universe has found itself a negative charge to partner up with, because the force of attraction is so powerful that over the billions of years that the universe has existed, that force of attraction has succeeded in partnering pretty much every positive charge with a negative charge, which means that matter in bulk is neutral. It's because the force is so powerful that it has neutralized itself. And yet, locked inside every one of our atoms is this immense force. We would just need to unbalance the positive and negative charges to release it. And that's what we do in electric circuits all the time. That's what potential difference is. It just momentarily unbalances the positives and negatives and causes a current to flow from which we invest energy, and we can extract that with our devices. So I want you to take home from this that the Coulomb force is vastly more powerful than the gravitational force. It's also comes in two varieties. The gravitational force is only attractive, and mass only comes in one flavor, just kilograms. Whereas the Coulomb force relies on an electric charge that comes in two flavors, positive and negative, resulting in a force that can be repulsive as well as attractive. I think that that's probably enough. So we're 40 minutes into the lesson. I think that's probably enough to introduce the Coulomb force to you. So what I think would probably be a good idea is if you were to just finish tidying your notes and do a couple of questions in the 20 minutes that remains. So if you could just scribble down to yourself that at the end of chapter 22.2, on the last page of 22.2, there are 7 questions, but I need you to skip question 5 until next lesson. So of the 7 questions, do them all except question 5. And then immediately above the questions, there is a summary table which collects together the similarities and differences between the electrostatic Coulomb force and the gravitational attractive force. So I have been through those similarities and differences with you verbally, but if you do want to collect it all together in a single table, then you could copy out the one that's immediately above the questions at the end of 22.2. Should you decide to read 22.2, which isn't necessary because I've been through it with you, it does start talking about electric fields, which I prefer to do after we've done the Coulomb force. So you're welcome to read that if you want, but that is the purpose of next lesson on Thursday. Okay, I'm going to leave it there for today. That's your introduction to the Coulomb force. Please tidy up your notes. Please do questions 1 to 7, omitting question 5 from 22.2. If you've got any questions, feel free to stay behind and ask them now. Otherwise,